Okay, welcome back from the coffee break. It's a pleasure to welcome Ilija Tolich, who's going to speak today on non-Hausdorff groupoids and purely infinite C-star algebras. Take it away.
Thank you very much. So as I said, non-Hausdorff groupoids and purely infinite simple C-star algebras. This is in-progress work with Lisa Clark and Astrid Dunhiff at the Victoria University of Wellington in New Zealand. So I'd like to thank the Fields Institute and the organisers for inviting me. So first, a quick rundown of what we're going to be talking today. We're going to go over some basics of groupoids, some of which we've already seen, but I wasn't sure quite what the background was when I was writing this talk. We're also going to talk about what we lose when we make the transition from a Hausdorff groupoid to a non-Hausdorff groupoid, and how that then cascades through the reduced C-star algebra, and what sort of changes we need to make that construction make sense again. Then we're going to move to purely infinite simple C-star algebras and what sort of groupoids can give rise to these things. And finally, we're going to end with an example on self-similar groups, which we also saw earlier today in Anna's talk. So first of all, a groupoid, as we've seen multiple times today, is a group with partially defined multiplication. So we have a distinguished subset G2, which is in a multiplication map that takes out these elements to the product alpha beta, and an inverse map gamma to gamma inverse, such that the inverse map is an involution, and if two products are composable, the product is associative and composable and makes sense as you'd expect. And element gamma is always composable with its inverse, and it undoes the action of gamma one-sidedly. We also have the units. So these are, we call this G0, the unit space. And this is all the elements gamma inverse gamma. So these are the analogues of the identity, as we saw on the previous slide. And so this is the unit space, and we call these elements units. And we define range and source maps from the groupoid down into the unit space. So that R takes an element gamma to gamma gamma inverse, and the source map takes it to gamma inverse gamma. So for a unit in our unit space, we talk about the isotropy group of U. This is all the elements in G such that the range of gamma and the source of gamma are the same and are equal to U. And so this is a group sitting inside our groupoid. And we talk about a set B being a bisection if the restrictions R restricted to B and S restricted to B are injective. And these sets are going to be really useful when we get our topology, because they're going to be what we want to form our basis of the topology. So we're in a C-star algebra world. We want to assign a topology to this thing. So a topological groupoid is a groupoid G with a topology under which the unit space G0 is locally compact and Hausdorff in the relative topology. So even though the talk is called non-Hausdorff groupoids, we do have a lot of Hausdorff behavior going on inside in relative topology. And the multiplication, inverse, and the range and source maps are all continuous. And further, we say G is étal if R and S are both local homeomorphisms. And so, as I mentioned, in this case, G has a basis of open Hausdorff bisections. So even though we've got a non-Hausdorff overall topology, there are a lot of Hausdorff places, and we're going to be restricting to those when we need to recover that behavior. We also say G is minimal if for all the units, the range of the inverse image of U is dense in G0. So this is all the groupoid elements that start at U and go to some unit. All of those units that you can reach from U are dense in G0. And equivalently, if you have an open set around a unit, then all the elements that you can reach from that open set, all the units you can reach, is the whole of G0. So now just sort of onto what we lose when we go to a non-Hausdorff setting. So most results for groupoids and C-star algebras involve locally compact Hausdorff-Ital groupoids. So when we go to non-Hausdorff, we immediately lose uniqueness of limits. Our unit space is no longer closed, so units can converge to elements outside of G0. Compact sets are not necessarily closed. And the product, sort of not defining that here, but it's the product by convolution of continuous functions may not be continuous. And so that's going to be a problem when we go to try and define our C-star algebra in a minute. But we do keep a lot of stuff because the groupoid operations play nicely with the non-Hausdorff elements. Because we had all our multiplication, inverses, range and source are all continuous with respect to the topology. So if we define a relation, this is an equivalence relation, between x and y, if any pair of neighborhoods of x and y, oops, sorry. Any pair of neighborhoods x and u and v around x and y overlap. So these are the equivalence classes is the non-Hausdorff points. So we call the set of problem points x with non-trivial equivalence classes p. And so we get a bunch of properties that sort of say, okay, yes, there's non-Hausdorffness, but we can sort of correct it or deal with it by looking at the groupoid operations. So if x and y cannot be separated by neighborhoods, if all their neighborhoods overlap, then they're going to have the same range and they're going to have the same source. If I've got x as a problem point, so it's a non-Hausdorff point, then everything that shares a range and a source is also going to be a problem point. For u in G0, for a unit, the equivalence class of u is going to be a subgroup of the isotropy group. And so that lets us, is going to be a little bit useful for detecting when a groupoid is non-Hausdorff, because if an equivalence u has a non-trivial equivalence class, if it's not separable from other elements of the group, of the groupoid, then its isotropy group is going to be non-trivial. And so that's sort of what we're looking for when we're looking to check when something's non-Hausdorff. Yes, I have not. It is. Sorry, there's a typo in the slides. Yeah. Sorry. Yes. So it is an equivalence relation. But yes. Sorry, it's non-trivial. So I should have signposted that better. And in particular, if you've got something compact in G, then the image of K under the range and source are compact and closed in G0 with respect to the relative topology. So you can get moved back into the unit space when you're worried, and so there you've got this nice Hausdorff behavior that you can work with and prove results. Now, the next element I want to talk about is 3 conditions on Ital groupoids. We've heard 2 of them already today. So we say G is effective if the interior of the isotropy of G, so all elements with the same range and source, is just the unit space. We say G is topologically principal if the set of units with trivial isotropy is dense in G0. And in particular, if you've got a set of elements with trivial isotropy, those can't be non-Hausdorff points. And we're going to introduce a third condition, which looks kind of similar, but not quite. G is topologically free if the interior of the isotropy of G less without the unit space is empty. And so we get this nice sort of diagram, which, so the green shows the implications for when the groupoid is second countable. The red shows the implications when it's Hausdorff, and the blue is just the implications in general. So if you have a second countable Hausdorff groupoid, you have all three of these coincide. They're all equivalent. If you've got only Hausdorff, then effective and topologically free are equivalent and implied by topological principle. If you've only got second countable, you've got equivalents of topologically principal and free, and both implied by effective. And if you relax your conditions completely, don't have second countable, don't have Hausdorff, you get effective implying topologically free and topologically principal implying topologically free, but you have no relation between the other two. And there are counterexamples of both of those relations. So they're completely unrelated if you don't have second countable and Hausdorff. So this is also kind of a bit of a propaganda piece of just sort of why topologically free seems to be the right one for the non-Hausdorff case. It lets us relax some of our conditions. But I haven't told you what the C-star algebra is yet. So for Hausdorff groupoids, we'd normally work with the continuous compactly supported functions on G. But as I mentioned, when you take the product of those functions with convolution, you don't necessarily get back something continuous, so it's not closed. So we introduce this sort of relaxation, and we take advantage of the fact that we've got a lot of open Hausdorff spaces running around. So we let C0 sub C of G is the set of complex valued functions such that there exists an open subset V in G. So V is Hausdorff, F vanishes outside V, and the restriction of F to V is continuous and compactly supported in V. So these elements here are all in C sub C of V for some open Hausdorff V. And we take the span of these functions and call it curly C sub C of G. And these functions, as the span of continuous things in a non-Hausdorff topology, these functions are not in general continuous. So we lose continuity, but these functions are closed under the normal convolution and adjoint operations on groupoids. So we lose continuity, but we keep the standard products and adjoints on a groupoid algebra, and the rest of the construction of the reduced C-star algebra can sort of proceed as normal. So we take, for every unit, we have left regular representations, LU from our curly C into the bounded operators in L2 of GU. So this is all the elements that have source U and that satisfy this this equation. And the reduced C-star algebra is just the completion of the image under the direct sum of all of these left regular representations. So lost continuity, but the rest of the construction goes through. Now, one of the nice things about functions is that we can look at what they're doing to particular group elements. Groupoid elements. We can look at what they're doing to particular subsets, and we can look at what their support is. So we'd like to recover that function behavior, but obviously our elements of our C-star algebra are not necessarily functions. They're their limits of functions, but we can use these left regular representations to construct an analog of the Renaud J-map for a non-Hausdorff groupoid. So for every A, we can define a function J of A from G to the complex numbers by this inner product. And in particular, if you started with something in curly C sub C of G, we have that J of F just gives us back that F. And Clark, Excel, Pardo, Sims, and Starling proved this is an injective norm-decreasing linear map from C star R of G to the bounded functions on G, which is a normed vector space on under the supremum norm. And so in the Hausdorff case, I think you get back to continuous functions on G, but we just get, we go to the bounded functions because we don't have that continuity anymore. So the benefit of this construction is that we can think of elements of this reduced C-star algebra as functions, and in particular, we can think about their support. So stepping back away from the elements of the C-star algebra, thinking again about curly C, so these are these spans of continuous, compactly supported functions on Hausdorff subspaces. So since we have each of these elements is a finite span of something with a compact support, we do actually have a compact K such that the support, so this is the open support in inverted quotes, the support of F is contained in some compact set, but because we don't have Hausdorff, our closure may not be compact and may not be contained in that K anymore. And the support of F might not be open and could have empty interior. And so that is going to be a problem when we go to look at ideals. So using the J-map, we can also consider the support of elements of a reduced C-star algebra. So let A in the C-star algebra, and we say A is singular if the interior of the support of J of A is empty. So the now these things are going to have, if I take a product of any of these things, I'm going to get, I'm also going to get something with a empty support. So one of these elements is going to generate a non-trivial ideal if there's any non-zero ones. So singular elements are one of the primary obstacles to simplicity of C star R of G. So this observation led to Clark, Excel, Pardo, and Sims, and Starling proving this first result. So let G be a second countable, locally compact Tolich groupoid if G is minimal and effective. So I've preserved the terms for each result, and so you sort of see why I needed to explain what each of these three are, because they sort of keep popping up, and they're all slightly different words. So we just end up with a lot of properties floating around in this talk, unfortunately. So if G is minimal and effective, and every non-zero element of the C-star algebra is non-singular, then the reduced C-star algebra is simple. Now, this also led to Excel Pitts and Kwasniewski-Meyer thinking about the essential C-star algebra. So this is the quotient of C-star R of G by the ideal of singular elements. So if you have Hausdorff groupoids, then this is just all of your elements of your C-star algebra are going to be non-singular because you're dealing with continuous, building it out of continuous functions. So they're all going to have open support unless they're zero. So in that case, the reduced C-star algebra coincides with the essential C-star algebra. There are some non-Hausdorff examples where these two coincide when there's no singular functions. But the power of this construction is it lets us state a much more clean result. So if you have a locally compact étale groupoid, if G is minimal and topologically free, so here we've gone to topologically free and we've lost the second countable condition, then the essential C-star algebra is in fact simple. So now that we've got sort of ways to make our C-star algebra simple, we want to look at, okay, how do we make these things purely infinite? So just a reminder, a projection P in a C-star algebra A is infinite if exists a partial isometry W such that P is equal to W star W, so the source projection, and Q is defined as W star is strictly less than P. So just as a note for a little bit of insight into where some of the conditions we're going to be looking at come from, is so just recall that this is the source projection, this is the range projection, and the idea is that the source gives you the whole thing and the range gives you something smaller inside or somehow contained in it. And we say that a simple C-star algebra is purely infinite if every hereditary subalgebra contains an infinite projection. So simple is doing a lot of work in that definition just to make the definition much more concise. So the first result we're going to be talking about is a condition from Ananthraman de la Roche in '97. So an étale groupoid is locally contracting if for every open set U in the unit space there exists some non-empty open set V and a bisection B such that the V is the source of B and the range of B closed in G0. So this G0 is just sitting there to make sure we're only closing in the Hausdorff unit space, is properly contained in V. So you can sort of see where some of this idea is coming from. You've got the source is the whole thing, and the range is smaller, contained, but related to the thing. And so her theorem. So if you've got a second countable Hausdorff étale minimal topologically principal locally contracting groupoid, then C star R of G is purely infinite simple. This was then extended. So for the non-Hausdorff case, so Kwasniewski and Meyer introduced this result. So let G be an étale minimal topologically free groupoid. So again, we've lost second countable, we've lost Hausdorff. If for every open U contained in G0, there exists an open V and finitely many bisections V1 such that V is equal to the union of all of these sources of BI, and that the ranges of the BI are disjoint and their closure is properly contained in V. So again, we have this idea of something, the source of which is the whole thing, and the range of which is properly contained. And then the essential C-star algebra is purely infinite simple. So this is actually in the original paper, this result is actually stated for Fell bundles and combines the previous result I attributed to them, but I've just sort of broken them up a little bit for this talk. And for Hausdorff ample groupoids, there is an additional restriction which gets this condition into an if and only if, but I've sort of elided that from this talk just because there's already a lot I sort of want to cover. But there is a sequence of papers, Renan, Sims, Benickley, Ma, and Arabaneki Bosseli, who all sort of contributed to this sequence and gave a very strong, a similar result for Hausdorff groupoids that we're now working to sort of convert to the non-Hausdorff case. So this is, I've called this a lemma because it's towards a future theorem that is not quite here. But I'd just like to illustrate the sort of, okay, we're kind of in, both of these theorems all sort of give this condition, then the essential C-star algebra is purely infinite. So we have a sufficient condition. It's not known what a necessary condition would look like, but given the sort of consistency of what these results look like, it sort of seems like something that looks like this is kind of on the right track. So I just sort of included this lemma. So if you've got a locally compact Tolich groupoid and C star R of G is purely infinite simple, then this is quite a weak statement. So for every compact open U in G naught, there exists finitely many bisections Bi such that U is equal to the union of the sources of Bi, and the closure of the range of Bi's is contained, not properly contained, in U. So you have kind of the flavor of what we've had before, but you're missing quite a bit of tech here, and so we're currently working to sort of strengthen this up, and I think we've got a slightly better result for ample, but it's not included here. So obviously, compact open, if you're in a general Tolich groupoid, that doesn't happen very often, and we're missing the ranges are disjoint, and you're missing proper containment. So before you could get towards a necessary condition. But just as a sketch of how this sort of thing works, so U is compact open. The characteristic function on U is then an infinite projection because C star R of G is purely infinite simple. And so we have some W in the reduced C star algebra that gives us 1U and something less than 1U. And if we approximate W by something in this compactly supported curly C, then you have the support of F is contained in some K compact subset. We can manipulate F or choose it so that the source of K is equal to U and the range of K is contained in U, and then a tight covering of K with finitely many bisections completes the result. And so this is sort of why this construction sort of I emphasize that these are the source and the range projections, just because this is how this proof goes, and in the other direction, how you construct your infinite projections from these bisections. So I'd like to end with an example. So this is another example we've heard already today. Self-similar groups. So I'm going to go into a bit more detail and use, unfortunately, very different notation. So let X be a finite set with more than one element, and let G be a group. Let X star be the set of all finite words, and let X infinity be one-sided infinite words. The pair GX is called a self-similar action if there's a faithful length-preserving action of G on X star. G takes A to G dot A, and for every G in a group and alpha beta finite words, there's some unique element of G restricted to alpha. So this is this price you pay by crossing through alpha. So G dot alpha beta is equal to G dot alpha, G restricted to alpha dot beta. So we can break down finite words into different group elements acting on the individual finite words. Now, we'd like to turn this into a groupoid, And ideally, we'd like this thing to give us a C-star algebra that's purely infinite simple. So what sort of groupoid do we want? We want to build a groupoid that encodes the map G from beta W to maps to alpha of G dot W. So it takes an infinite word and does the action of G on it. And you've got two sort of chosen prefixes that are just left alone. And we'd like it to compose. So if you have something delta V, so a finite word, infinite word, the action of H takes it to some other finite word as a prefix, and then H dot V. We'd like something to compose if the two infinite words match up, and then G takes it to alpha G dot W. Excuse me. And we also want our maps between two infinite words to not depend on how we use the restriction. We want, so if we've got, for example, alpha G dot epsilon W from beta epsilon W, so this takes epsilon W to G dot epsilon W. It doesn't matter if I do it that way or if I write it as taking alpha of G dot epsilon to be my new prefix, and I only apply G restricted to epsilon to W. So this, I want these two maps to be equivalent in our groupoid. And so unfortunately, this is quite a nasty way of writing it, just because there's quite a bit of information we need to encode. This groupoid is more usually presented as a inverse semigroup groupoid, but just because I'm not as familiar with that, I've rewritten it as something that looks a little more like a transformation Diacono-Renaud groupoid. So set is just going to be elements with finite word, group element, finite word, infinite word that extends this finite word. And we define an equivalence between these if the two infinite words are equal. So if they're if they're coming from the same infinite words, and depending on which one is longer, if they respect the restriction. So if beta is longer than mu, then mu must have an extension epsilon, and then alpha has to equal gamma concatenated with H acting on the extension, and that H restricted to the extension has to equal G. So depending on which way around you get two equivalences. And again, apologies for the notation. So the elements under this equivalence relation form a groupoid, and there's a lot going on here. So I just like to draw attention to some particular bits. So the source of an element of the groupoid is just going to be the infinite word. So as you might expect, we want the source of this groupoid element to be this thing over here, and then the range also to be this thing over here. So the units are just the identity, empty prefixes, and just some infinite word. So the source is just beta W, the range alpha of G dot W, and the inverse just sort of reverses the map along with inversing the group element, and just sort of the reverse of this action. That gives you the range as you know your infinite word you're mapping through. And the two elements are composable if the infinite word on this one matches up with where I'm mapping the infinite word. So beta W is equal to the image of this delta V, so gamma of H dot V. And this condition just, this multiplication just depends on which one is longer. So as I mentioned, the unit space, all we're really encoding is the infinite word. So this is all elements of the form empty prefix E, empty prefix W for some infinite word W. And the topology of this thing is generated by a basis of compact open sets. So we're taking, this almost looks like a groupoid element, but this is actually a finite word. And so it's all extensions of that finite word that are also extensions of this beta element. So it's just all groupoids with the first three coordinates the same and a different extended infinite word. So Clark, Excel, Pardo, Sims, and Starling showed that this groupoid is minimal and effective, and hence it's also topologically free. So immediately you get that the C-star, the essential C-star algebra of this thing is simple. And now we want to know, A, is it non-Hausdorff? And is it going to be purely infinite simple? So when is this thing non-Hausdorff? So there's a lot going on in that multiplication, but if we have an element G in G and an infinite word that's fixed by G, so G dot W is equal to W, and for every prefix alpha of W, this restriction is not equal to the identity. So even though something is fixed, an infinite word is fixed, that doesn't necessarily mean that G is just going to fall our way into the identity. It could still be doing other things elsewhere. And in this case, we have the unit at W is not equal to this empty word G, empty word W. So these two things are not equal, but they're isotropic. They both have the same range and source. And so this is, as I said, this is where we'll go looking for non-Hausdorff elements, can I separate these two elements? So every neighborhood of GW contains a bisection of the form ZG alpha for some prefix alpha of W. And so this is kind of this condition of when is it non-Hausdorff. So if you have every prefix alpha of W has some extension alpha beta, where the restriction of G to alpha beta is just the identity, then this groupoid element is going to be inside this basis element, inside this compact open set around GW. But since G restricted to alpha beta is the identity, under the equivalence relation we defined, these two things are actually the same. So this thing is actually a unit. So these two groupoid elements are equivalent. And so in this case, where every prefix of W has an extension that sends G to the identity, every neighborhood of GW intersects the unit space, and hence G is going to be non-Hausdorff. This one. So, no, sorry. Yes, actually, yeah.
Because you can have 3 points and one sequence converges to the first two, and a second sequence converges to the second two, and nothing converges to the first and last part.
I think the groupoid fixes that, but
well, maybe for completely for groupoids, that's why we say the alpha space has to be Hausdorff.
Yeah.
Okay, so maybe for groupoids, you get
Yeah, no. Yeah, I'll. Sorry, yeah, I'm pretty sure. I'm pretty sure the groupoid, as I said, like the groupoid plays quite nicely with the topology. So I think that's fixed unless anyone's. But sorry, I'll have to think about that more often. So yeah, so this is the groupoid equivalence relation. Means that this thing is actually a unit, even though it's sort of right next to something it's not a unit. And so every neighborhood of this GW is going to have something like this in it, a unit is going to intersect the unit space, and hence the unit space is not closed, and then the groupoid is non-Hausdorff. So there are examples of self-similar groupoids that are self-similar groupoids that are Hausdorff, but we can't guarantee that, and there are interesting examples that are non-Hausdorff. For example, the Gregorczyk group. And then finally, the essential C-star algebra is purely infinite simple. So how do we show that? So we've got our self-similar group GX. So we're going to fix an open set, and we're going to show it's locally contracting. So fixing an open set U in G0, then there exists an open subset of the form Z E alpha contained in U. So there's one of these basis elements is in there, and as it turns out, we can take some bisection B that just takes all extensions of alpha and maps them from alpha to alpha x1. Takes the infinite portion and just adds an x1, so it extends it a little bit. And so the range of this thing is going to be just the cylinder set with alpha x1. This is strictly contained. It's also closed because it's compact in a Hausdorff set. And so it's strictly contained in Z E alpha, and the source is just back where we started. So immediately we have that it's locally contracting, and as we showed before, it's minimal and effective, hence topologically free, and so we get the essential C-star algebra being purely infinite. So what I'd sort of just like to end on what we're working on now. So currently it's not known whether these contracting conditions or related conditions like paradoxicality or when a groupoid itself is purely infinite, which is a slightly different definition that implies the C-star algebra is purely infinite. It's not known when these are necessary for the essential C-star algebra or the reduced C-star algebra to be purely infinite. And in the Hausdorff case, conditions for G are known such that the reduced C-star algebra is either purely infinite or stably finite. So this is something I didn't really go into in this talk, but we're currently working to extend this dichotomy to non-Hausdorff groupoids and the essential C-star algebra. So I'll end there, and thank you for your time.